Electric trains actually work. Let's follow the electricity from the power plant all the way to the wheels and understand the electrical network that makes modern rail possible. It all starts with the power chain. A power plant generates electricity. It enters the national grid at high voltage. Traction substations along the railway step it down and convert it. The electricity then flows through overhead wires or a third rail to the train itself. Each stage transforms the voltage to match what comes next. Traction substations are the link between the national grid and the railway. They take grid power, often at 110 to 400 kilovolts, and step it down using transformers. For DC railways, rectifiers convert the AC into direct current, typically at 750 or 1500 volts. These substations are spaced every few kilometers to tens of kilometers along the line, and they include circuit breakers and protection relays to isolate faults instantly. Power reaches the train in two main ways. Overhead catenary uses a wire suspended above the track. A pantograph on the roof of the train slides along this wire to pick up current. This is common for mainline and high-speed rail, usually at 25 kilovolts AC. The other method is the third rail, an electrified rail running alongside the track. A collector shoe on the train makes contact. This is typical for metro and subway systems at 600 to 750 volts DC. In both cases, current returns through the running rails to complete the circuit. Different railways use AC or DC, and there are good reasons for both. AC systems, especially 25 kilovolts of 50 Hz, are the modern global standard. AC is efficient over long distances and substations can be spaced far apart. DC systems like 750-volt third rail are simpler and were historically easier to control. They're still widely used in urban transit. Modern trains often carry onboard converters so they can operate on either system. Inside the train, power goes through several conversion stages. If the supply is high voltage AC, a transformer steps it down first. Then a rectifier converts it to DC. An inverter takes that DC and creates variable frequency three-phase AC. This feeds the traction motors that drive the wheels. By varying the frequency and voltage, the inverter gives precise control over speed and torque, no mechanical gearbox changes needed. Modern traction motors are three-phase AC induction motors or permanent magnet synchronous motors. They deliver maximum torque from a standstill, which is perfect for accelerating heavy trains. Efficiency exceeds 90%. And here's the key advantage: they can run in reverse as generators. When the train brakes, the motors generate electricity instead of consuming it. This is called regenerative braking. Regenerative braking is one of the biggest advantages of electric traction. When the driver applies the brakes, the traction motors switch to generator mode. Kinetic energy from the moving train is converted back into electrical energy. This electricity is fed back into the overhead wire or third rail, where it can power other trains on the same line. On average, about 30% of energy is recovered this way. It also reduces brake pad wear, saving on maintenance. Put it all together and you have a complete electrical network. Power plants and renewables feed the grid. The grid feeds traction substations. Substations feed the catenary or third rail. Trains pick up the power, convert it on board, and drive traction motors. When braking, energy flows back. And the whole system is monitored and controlled in real time by SCADA systems that balance load and detect faults across the entire network. From power plant to wheel. Pure electricity. Electric trains are one of the most energy-efficient forms of transport ever built. Behind every smooth ride is a precisely engineered electrical network, generating, converting, delivering, and recovering power at every stage. The grid moves the train. The train feeds the grid.